Hello everyone, welcome to the lecture series on Fundamentals of Generative AI and Large Language Models. We are in the week 4 and this week 4 is all about the advanced variational autoencoders and practical applications. So far in the last week, in the week 3, we have seen in detail about how VAE works, and then we had solved one numerical example, and we had seen one of the most important concept called reparameterization trick. So with this we will start with the week 4, and in week 4 the following are the contents that we will be covering. So if you have seen in the week 3 we had not seen any practical implementation. So this week 4 we will be starting with the hands-on implementation of VAE, and then we will be seeing some of the important concepts such as entangled and disentangled latent space, and we will see something called as Beta-VAE. Then we will move towards the conditional VAE. When we are discussing the conditional VAE, we will also see what is the motivation, why is that we have to go for conditional VAE, and we will see the loss function of conditional VAE, and there also we will see one numerical example. And towards the end of this particular week, in a theory session, we will see the next important concept called latent space interpolation. So, once we see the theory concepts of these, we will see an hands-on implementation on Beta-VAE and conditional VAE. So this is all the outline of this particular week 4. So let's get started with in this particular session we will see something called as entangled and disentangled latent space, and then we will connect something called as Beta-VAE. Okay, so although this particular slide looks very heavy, but listen to this very carefully, it is very simple concept. Now what we are discussing is an entangled latent space. So latent space is not something new to us. So how is that we get the latent space? Now we are passing, there is some input, that input is passed to the hidden representation. Here hidden representation has totally 8 neurons. Then is it not H1 is the combination of all this input x1 to xn? Similar way, all the hidden neurons will have the combination of all of these inputs. Okay, what is that we are discussing? We are discussing VAE. Now, in VAE, how is that we are going to get the Z? Z is obtained using reparameterization trick. Z is obtained using a formula. This is the formula which is used to get the Z, which means the encoder also should produce us the mean and variance, right? So we have from H we are going to get this mean and then the variance. Now how is that you will be establishing the connection? Is it not the connections are established in this way, right? So now once we establish a connection like this, we have already seen in our previous week 3 last session where we have solved the numerical example. So recall that particular concept. We have now obtained mean and then the log variance. From log variance you will convert into variance, from variance to standard deviation. Okay. So once this is done, is it not Z is now sampled using this particular reparameterization trick formula? Now in this, what are we understanding? Now when I get that Z, that Z is the combination of many of the important or many of these inputs. So can I say, because this mean whatever we have obtained, this mean has the combination of all of these, and all of this is the combination of this entire. So now can we call Z as the latent space? Yes. Or latent variable? Yes. So now if I take Z1, the latent representation Z1, Z1 is the combination of all of the important variations. Then Z4 till Z4, Z4 is a latent representation which is the combination of all of those input. Okay, so I hope you have understood this particular concept. Now, when we say Z1 to Z4, what is the meaning of this? The meaning of this is, let the input be of any dimension, let the input be of any size, but in that input there will be few important variations or important characteristic in that particular data. So, here Z1 to Z4 we are calling it as a latent representation. The role of a latent representation is to get that compressed representation of an input. Okay. Now, is this diagrammatic explanation, is this clear? Input is passed to an hidden representation, because a hidden layer, it is all of the neurons are connected to every of the hidden neuron. So, when I say H1, H1 is the combination of all this X1 to Xn. Similar way, H8 is a combination of all of this. From H1 to H8, you are getting a mean and then the variance. So, can I say that the mean, whatever we have calculated, it is the combination of all of this? Yes. So, variance what we have obtained is once again is the combination of all of this. If mean and variance what we have obtained is the combination, from there when you get Z1, do you agree that Z1 is having the combination of all of those features in a much compressed form? Agree to this, right? So, now let us say this is all about the latent space. Now, you are convinced that Z1 is the combination of many, right? Now, let us go back and then see now what is being written in this particular slide. Let us consider there is an image of size 28 cross 28. We have considered an MNIST data set, which is a standard handwritten digit, which is of size 28 cross 28. Now, I am converting that into a single vector. So, single vector, it is of size 784. Okay. Now, if you look into this particular image, not all 784 pixels gives us some information. There are only few important characteristics or important variations in this particular data. What is that variation? What is the thickness? Whether it is a thin or a thick. Then whether it is a slant or whether it is straight. Then what is the rotation? Position. These are some of the important variations which are present in our data set. For example, one more, if I have to give you an example, which we will be seeing in the next slide. When we have so many human beings, face data set, what will be the important variations? Is it not the important variations will be the skin, then the hair, it can be a smile, or it can be the pose in which the person is giving, or it can be the light, what is the amount of light. So, even though you have a data set, there will be some of the important variations in that particular data set. Okay. So, I hope this concept is clear to us. Now, let us assume those important variations are these four. What are those four? This thickness, slant, rotation and then the position. These are the four variations that we have. Now, what is that we are doing? In VAE, we are discussing all about the VAE model. The encoder maps the input to whatever is the input, it is mapping to these distributions. Yes. So, now suppose if you keep a latent space as 4, if the dimension is 4, then what is this 4 Z1, Z2, Z3, Z4 are the 4 latent representations. I hope this is clear to us. Now, since a hidden layer has 8 neurons here, this 8 is the combination of all X1 to X784. Agree to this? Similar way, H8 is the combination of all X1 to X784. If that is the case, do you agree to this concept? That is Z1 to Z4, it is a mixture of, it is the combination of all of those, that is the thickness, slant, rotation and position. Do you agree to this? Yes? Because Z1, Z2, Z3, Z4 are the latent representations, which is responsible for capturing the important variations in the data. Now, if at all if there are 4 variations and this Z1 to Z4 is the latent representation which is also having a 4, then Z1 is just not 1, it is the combination of all of those. Agree to this? Why it is combination of all of those? Because H1 to H8 is a combination. H1 to H8 when it is passed to mean and variance, there also it is the combination. From there when you get a Z1, it is once again the combination of all of these 4. This is important concept, you need to understand this. So, this is called an entangled latent representation. What is entangled latent representation is, now changing one latent variable will change the multiple properties together. So, what is the meaning of it? Now, if you take a Z1, Z1 has some portion of thickness. It has some portion of the next slant. It has some portion of rotation, and it has some combination of a position. Now, what is entangled latent representation is, you look at this Z1. Z1 is a combination of all of these variations. Now, if I want to do some modification to this Z1, I want to change some value, some modification you want to do to this Z1. Then if you do the modification to Z1, it is having an impact on this, it is having an impact on all of these. So, changing one latent variable may change multiple properties together. Okay. Suppose if this concept is not very clear, probably when we see what is disentangled, you may understand this. From this particular slide, understand only one concept called entangled latent space. What is entangled latent space? Z1 to Z4 is the latent size. Now, each of these latent variable is the combination of many of such important variations. So, by doing one small modification, you will have an impact on all of those. This is called entangled. Now, further if you have to understand, this is look at this particular diagram. Now, when you see this first, this is all the human face. In this, what are important variations? The important variations are hair, then what is the amount of lightening on the face, skin, smile and pose. These are the different important variations in this particular data set. Now, can we have a model, or how about this architecture? Now, if you look into the first set of images, the person is the same, here the person is the same, person is the same, here also, here the person is the same, but what has changed here? If something has changed, it is only the hair. Now, if at all, if we can capture, if we can do a modification only with respect to hair, is it not we are getting multiple variations of same data, and each of this variation is different from each other? Is it not we are generating more such data? Now, look at this particular smile. When you see this, here the person is the same, but look at the first image, look at the second, third and fourth, as and the difference is only change in the smile. By changing only one parameter, you are able to generate a different variation. Similar way, look at the pose. Now, when you look into this, here once again the person is the same, but this particular variation, if you can able to modify only this, keeping rest of the parameters same, is it not we are getting a different version? So, this concept is good, right? It is more convenient to get more amount of data, or to generate a different variations in the data, right? So, now what is this concept is all about? You have a hidden representation, that you have a latent representation. What is this latent representation here? It has to capture the important variations. Sometime back we have seen that those hidden representation is capturing, but there is a combination of many of these important variations. Z1 is having all of these variations in different combination. Z2 is also having all of those important variations. Instead of that, can we do something like this? If at all, if I have an latent representation size as 5, and if here the important variations here are 5, can I make the model where each of the latent representation is primarily focusing only on one variation, which means the latent representation Z1 is primarily focusing on hair, Z2 is primarily focusing on light, Z3 on skin, Z4 on smile, and Z5 as the pose. If you can able to achieve this, if we can make each of the latent representation to capture only one of the important characteristic of this variation, then what is that we are going to achieve? So here if at all if you want to do this, then each latent variable mainly controls only one factor of variation. True. Now by doing this, now when we change only Z1, look at this. Now when we modify only Z1, which means only hair is getting modified, then rest of the concept is remained same. So therefore, if you change only Z1, mainly the hair related feature should change. Other factors such as lighting, skin, smile, and then the last characteristic, everything should remain unchanged, mostly unchanged. If we can able to do this, then what are we achieving? Is it not we are manipulating a specific latent variable? By manipulating only a specific latent variable, the model can generate the variations in the image. Now if I am changing only the hair in this particular one, is it not I am able to control, I am able to generate the different variations in the image, and is it not it is going in a much controlled way? Is this concept okay? Right, how to do, we will learn that, but is this concept of did you get this concept? Now if you can anyhow latent representation role is to capture the important variations in the data in a lower dimensional space. Now anyhow it is capturing, can we enforce, can we ensure that each of the latent variable should be responsible for capturing only one of the variant, one of the important characteristic? If we can achieve that, then that is called disentangled latent space. What is a disentangled latent space? It is a latent space where the primary aim is to learn the structured representation. What is a structured representation here? Where each of the latent dimension is focusing only on one factor of variation. Let any number of variations be there, but each of the latent vector is responsible for capturing only one important variation. So I have given the same example here. Suppose if you consider 5 latent size as a 5, then we have totally 5 different vectors Z1, Z2, Z3, Z4 and Z5. So our primary aim is Z1 should focus only on the hair, Z2 should be focusing only on lighting, Z3 should be focusing on skin tone, Z4 on smile, and Z5 on the pose in which the face is. So if these are the meaningful factors in the image, then we want each of the latent vector to focus only on capturing one of that important. So what is our ultimate aim? Ultimate is it not the ultimate aim is by changing only one, we are keeping the rest of it same. So changing one latent vector changes only one particular that factor, which means if you are increasing Z1 or if you are changing Z1, only hair related variation changes. Similar way, when we change only Z2, only lighting should change, the rest of it should remain the same. When we take Z3, skin tone should change, but the rest of it should remain. That is the reason if you go back and then look into this diagram, So if you are looking into, there is only a smile which we have considered, and only this particular z is being modified, or it is been changed. By changing that, rest all of the factors has remained the same, only the smile has been modified. This is called disentangled latent space. So where you are if you change only one latent variable, then mainly only one property of the generated image should change, and the rest of the features should remain the same. So if you look into this, so mainly only one property of generated image should change. So all these are the generated images, and only one parameter has been changed. What is that parameter? It is only the hair which has been changed, and rest all of the properties has remained the same. So do you agree to this particular concept? This is called an disentangled latent space. So by doing this, we are going to have an interpretable and controlled latent space, and this is called disentangled latent representation. I hope this concept is clear to you. Now, how do we achieve this? Okay, latent representation Z, so far whatever we have seen, it is an entangled. So if that is the case, how do we achieve the disentanglement? So in a standard VAE, the loss function is this. We have a first term as reconstruction, and the second is the KL divergence. To this particular loss, we are adding one regularization parameter called beta. So adding a weight beta to a KL divergence term. So this is what is Beta-VAE, where the only difference here is there is one regularization parameter, that is beta is being added to the KL divergence. Now if that is the case, let us understand how it is going to achieve this. Okay. Now, what is the first term here? The first term is a reconstruction. What is a reconstruction? Primarily ensures that it ensures that the decoder reconstruct the input. So which means whatever the reconstructed data, that should be approximately closer to the original input, which means the latent representation Z. How do you get the decoder? How decoder will reconstruct? Is it not Z should be passed as an input to the decoder? If Z is very good, then definitely decoder can reconstruct the input, reconstruct the data well. So which means store enough information in Z so that the decoder can able to reconstruct it. Okay, let us now look into the second term. What is the second term here? KL divergence. What is KL divergence says? It always encourages the encoder distribution should remain closer to the prior distribution. That is what the second term KL divergence says. So now which means do not store the information in an arbitrary way. Why? Because if you store it in an arbitrary way, then definitely the the distribution, the difference between these two distribution will be very high. So one term is saying that store enough information in Z so that I can able to reconstruct well. The second term is saying do not store the information in an arbitrary way. So which means there should be a good balance here, and that balance is there has to be a good reconstruction, but at the same time we should have a regular latent space. Okay, now you can ask this particular question. What is the difference? Even in standard VAE also the loss, we have seen that reconstruction loss and KL divergence. So all this is doing even in standard VAE also. Then in what way it is different is, look at the loss function very clearly here. What is, if nothing is there, can we assume this as 1? If it is 1, can I say that the beta term here is 1? Right? So whatever is the beta value in a standard VAE, beta value is 1. So which means model can allow the latent representation to have some mixture. What is that mixture? We have seen some time back the combination of many of those important variations. As long as it is helping you for a good reconstruction, go ahead and then have some combination, the latent representation can have some combination, which means it is primarily, not primarily, it is, we can say that it is an entangled latent representation. So, which means it does not guarantee the disentanglement. In a standard VAE, there is no guarantee that there is a disentanglement. What do you mean by disentanglement? Each of the latent representation should capture only one variation. Standard VAE, beta value is 1. Because beta value is 1, there is no guarantee that the scale divergence, when beta value is 1, there is no guarantee that the latent representation is disentangled. You can have the combination, you will have the mixture of the important variations which are present in the latent representation. Therefore, it is an entangled latent representation, but it does not guarantee the disentanglement. If you have to achieve disentanglement, what is the only possibility? What should be the beta value? The beta value should be greater than 1. Right? In Beta-VAE, beta value will be always greater than 1. Now, just imagine what will happen if beta value is greater than 1. Is it not more importance is given to the KL divergence here? When more importance is given to this, is it not little more extra pressure is given to the model? What is that pressure? The pressure is definitely the encoder distribution should follow the prior distribution. Is it not? This is the meaning that we are getting. Okay. So, when KL value, when beta value is greater than 1, KL term is given more importance, which means a larger KL weights, there is more pressure that is being put. And what is that pressure here? Encoder distribution should stay closer to prior distribution. Right. So, what do you mean by this? It strongly encourages that the mean value should be closer to 0 and then the variance should be closer to 1. So, this restricts the model from freely storing mixed information in all the latent variable. So, this is the place where you are restricting the model to store mixed information in the latent variable. So, this is the Beta-VAE, where the loss function will remain same exactly as standard VAE, but there is one regularized term called beta, and beta value should be more, and what is more should be greater than 1. When it is greater than 1, how is that we are achieving? There is a little more stronger pressure on this particular term. What is that? Encoder distribution should stay closer to prior distribution. When you are enforcing that, this ensures that the model does not capture too much of mixed information at a latent variable. Right. So, now the next concept here is, so just by having the beta term here, are we very sure that the disentanglement is achieved? There is no guaranteed that perfect disentanglement is achieved. So, you are encouraging the disentangled latent space by applying a stronger regularization, but however, there is no perfect, there is no guarantee that you will achieve the disentanglement here. Now, so can you think, okay, if disentanglement is not guaranteed, can I increase the beta value so that definitely disentanglement is achieved? Answer is no. If you make beta as a too large value, then what is that you are doing it? You are compromising on the reconstruction quality. So, the reconstruction quality may decrease. When reconstruction quality decreases, definitely the reconstruction loss increases here. So, this is what is an issue. Now, how is that we are little more, let us have a little more clarity on whatever is the theory concept that we have seen so far. So, let me summarize before we get into a numerical intuition or example. The whole idea here is you want something of this. Let us go back and then our aim is, if we have our model where each of the latent space captures the important variation, and every of the vector is responsible for capturing only one of the variation. If that is achieved by doing modification only with respect to Z1, you can able to generate different variations. So, this is our requirement, and this requirement is achieved by using the KL beta term is added to an KL divergence. Now, how beta is going to control here is, if beta value is greater than 1, this entire KL term becomes more. When KL term becomes more, which means a stronger pressure is being put to the model that both the distributions should remain closer to each other. This is the restriction which we are putting. This restriction ensures the model does not capture, that is the hidden representation or the latent representation will not have too much of a combination, but it tries to go for an single important representation. Now, let us look into, and from this what is that we have understood, although Beta-VAE does not guarantee the perfect disentanglement. If we try to increase the beta value to a larger one, then the reconstruction quality will be compromised. Okay. Now, let us take one small example, so that you will be able to connect with whatever the theory that is being explained. Now, let us assume our latent space size is 2, just for an understanding. If it is 2, then is it not Z1, Z2? How is that you get Z1, Z2? Is it not mean 1 plus standard deviation 1 and then the epsilon 1? Z2, is it not Z2 is obtained from this particular formula, and epsilon 1 and 2 are sampled from normal distribution. Okay. Now, what is the possibility? The possibilities are either entanglement or disentanglement. Now, let us assume ideal case where it is disentangled latent space. If it is a disentangled latent space, which means Z1 is responsible only for one factor, Z2 is responsible only for one factor. So, can I say Z1, for example, Z1 is responsible for thickness, Z2 is responsible for slant. Now, how do you get this Z1 and Z2? Is it not you are getting Z1 and Z2 from mean 1 and then standard deviation 1, and Z2 is from these two, right? So, in an other way, is it not if Z1 you are calling it as disentangled, which means that mean 1 is mainly primarily focusing on thickness? Then only Z1 can be only on thickness, right? So, can we say Z1 is focusing, if it is focusing on thickness, and if Z1 is obtained from mean 1, then mean 1 is also focusing on thickness, right? So, mean 1 mainly encodes thickness, and Z2 carries the slant information, therefore, mean 2 is also focusing on this. Okay. So, what is the hidden intuition? Mean 1 is capturing only little information. What is that little information? It is capturing only thickness. Mean 2 is capturing only little information, which means it is capturing only thickness. That is a slant. So, if it is capturing small information, is it not the mean values should be small? Can you understand in this way? So, if Z1 should focus only on thickness, Z1 is obtained from mean 1, then mean 1 should is capturing only a small information. What do you mean by small information? Only one information. So, here mean 1 and mean 2 values are small. Why small? Because it is focusing on capturing only that particular information. For simplicity, we have assumed the second, that is variance, as 1. Just for an simplicity for calculation. So, when you calculate this, is it not this is a KL divergence in a closed form? So, since this variance value is 1, so substitute the values in this. This is 1, log 1 minus 1, log 1 is 0. So, 1 minus 0 minus 1, that entire terms gets cancelled. So, KL divergence, you are left out with only the mean value. Since the latent representation is 2, therefore, we are taking both mean 1 and mean 2. So, here the value is 0.4 and 0.2. Just for an example, substitute the values. KL divergence value what you have got is very less. So, from KL divergence value, when you have got very less, what is the ideal meaning of this? Can you go back and then understand what is the meaning if the KL divergence value is less? It means encoder mean or encoder distribution is very much closer to the prior distribution. Is it not? The distribution is closer to the prior distribution. So, if it is very much closer to the prior distribution, when this is possible? Only when the mean values are less. If the mean value is less, is it not that it has captured the less information? Are you able to backtrack and then do the reverse engineering explanation here? So, I am bringing back once again. So, here we need to understand how it is ensuring that Z is focusing only on the one variation. So, if Z is focusing only on one variation, which is on thickness, is it not that thickness Z1 is obtained from mean 1? If Z1 has to focus only on this, is it not mean 1 also should focus only on this, mainly encodes thickness? If that is the case, is it not it is carrying only one information? If it is carrying one information, can we say that the value is small? If the value is small, then what is that it is giving us the information? Overall KL value is less. If overall KL value is less, what is that? It means that the encoder is closely matching with the prior distribution, which means the mean value is closer to 0. If the mean value is closer to 0, which means that can we say that these mean values are taking only less information. If it is less information, is it not that Z is focusing only on one parameter? I hope this is clear. Let us take one more example where it is entangled space. Now, what do you mean by entangled? Entangled means since the latent representation size is 2, so Z1, Z2. Z1 should be combination of both, Z2 should be combination of both. Okay. If Z1 is a combination of both, then mean 1 also should be the combination of both. If Z2 is the combination of both, then mean 2 also should be the combination of both. If that is the case, definitely the value will be higher. Look at this, the value will be higher. If the value is higher, can we see what will be our KL divergence value? Here the KL divergence value, can you see? The value is high, where you are getting KL value as 0.50. So, here once again mean value what we have considered is 0.8 and 0.6. Substitute the values back into this equation. So, taking the square of it, it is 0.64 and 0.6 square is 0.36. Add up these two and then the KL divergence value is large. When KL divergence value is large, what is that we are understanding? Here it is 50% of it. So, what is that we are understanding? Is it not that the encoder mean is away from the or far from, not away, far from the prior distribution? Now, how can you say it is far from the prior distribution? If it is closer or if it is nearer, then the mean should be closer to 0. But do we have our mean closer to 0? No, the mean values are not closer to 0. If the mean values are not closer to 0, it means mean value is more. What is the meaning that mean value is more? It has captured more information. So, here the distribution is far from the prior and the encoder is using more is using a more latent capacity to store the information. Now, let us take one more example, and so that you will be further convinced. Here further mean has increased. If mean has increased, then what is the meaning of it? The encoder distribution is far from the prior distribution. If you look into this particular example, here it is 1.5, when you square it, it is 2.25, then the second is 0.5. So here the KL value is very large. When KL value is very large, what is the meaning of it? Encoder distribution is far from the prior distribution. What is again the other meaning? The mean of it is far from the normal distribution 0. If it is far from normal distribution, look at the value is very high. If the value is very high, it means that it is capturing more information. If it is capturing more information, definitely from there Z1 whatever you get, that is the combined one. So this is an entangled, right? So I hope this is clear to you. Now I have one particular problem here. Now what is this? Suppose you have an image where in the image you have less number of important variations, and you have almost the latent dimension similar to that, which means whatever example that we have seen so far, that example had 4 important variations and a latent space also had Z. So because of latent variable Z also had 4. So because of this, there can be a possibility that entanglement is disentanglement is possible, because it is one-to-one mapping. But can we consider this scenario where in the image the number of variations are large? There are many such important variations. For example, look at this. You have the important variations. There are 6 such important variations. Now, so far in our understanding, we had taken equal number. But what now you have in latent space which is smaller than or lesser, latent space size is lesser than these important variations. So here the variations are, latent size is only 3. What is the possibility? There are 2 possibilities. What is the first possible? Allow the entanglement to happen. That is one approach. So the first approach is allow the entanglement to happen. If you allow the entanglement to happen, then only it can able to capture all of those information. If it captures all of those information, then only the reconstruction will be proper. So if you allow the entanglement to happen here, this is the only solution that we are able to see at this point of time. Otherwise, the number of variations are more. Z is small. If you allow the disentanglement, then it is going to capture only few, remaining are left out. So if you allow the entanglement to happen, then is it not Z1 is the combination of all of those features, Z2 is the combination, Z3 is the combination, all of the features have been captured. If all of the features have been captured, then what is very good? Reconstruction is good. So if this is the case, since the model is storing more information, reconstruction will be better. Therefore, reconstruction loss will be lower. But what is the problem? Sometime back in our example we have seen, if it has captured more information, what will increase? The mean value will increase. When the mean value increases, it is definitely far from the prior distribution, which means KL divergence value. What is that? See, because the latent variable is carrying more information, then the encoder distribution may vary far from the prior distribution. If that is the case, what is going to happen? Is it not the KL divergence value increases? We have seen in 2 examples in the previous slide. KL divergence value increases. If a KL divergence value has increased, which means what? So if a disentanglement should happen, then definitely beta value should be greater than 1. So in this particular case, what will be the beta value? Beta value will be small, will be very low, because there is no disentanglement, it is entangled. When it is entangled, beta value will be smaller. Is this example is clear to you? There is one scenario where the number of input features, important features are greater than the latent size. If that is the case, one scenario is entanglement, one solution is entanglement. If you allow the entanglement to happen, then KL divergence increases. So then what is that you have to do? You have to go for disentanglement. You have to encourage to go for disentangled latent space. Now, what is the problem here? If you go for disentangled latent space, now there are 6 such important features and the latent size is only 3. If that is the case, is it not only among this what is the most important, it is going to capture those features, and the remaining are not at all being used or not at all being captured? If it is not captured, is it not the Z is very weak? If Z is weak, if Z is passed to a decoder, then reconstruction will be very poor. In this particular scenario, what is going to happen? Is it not reconstruction loss increases? Definitely reconstruction loss increases. Why? We have bad Z. When Z is poor, when that Z is passed to an decoder, reconstruction will be very, reconstruction loss will be very high. So now, because it is a disentanglement, beta value is greater than 1. If the beta value is greater than 1, what is that we are ensuring? That the mean value should be closer to a prior distribution. That means the KL divergence value will be very less. So in this particular scenario, what is going to happen? That KL divergence value may decrease. So here there is a high beta value in this particular scenario. Because there is a high beta value, more emphasis is given. Because it is more emphasis, so definitely this distribution should stay closer to this, which means the mean value will be closer to 0. When mean value is closer to 0, when you calculate the KL divergence term, the KL divergence term decreases. With this, can we ensure that Z has focused only on a few? Reconstruction loss has increased, KL divergence term has decreased. Before in the previous example, what has happened? Reconstruction loss has decreased, but KL divergence term had increased. So in this, both are not the solution for a given scenario. Then what is the solution? In such a particular case, one of the possible solution is increase the latent space. Now, how do you ensure that how much to increase? It is just a trial and error. It is a hyperparameter, increase the latent space size. So, by increasing the latent space, we will be able to capture more features. So, you think of disentanglement. So, more such features will be captured. When more such, reconstruction loss will decrease. When reconstruction loss decreases, anyhow KL divergence term is also decreased, right? So, this is what is one possible solution. But here this requires you have to go for it's an hyperparameter tuning. So what is the second possible solution? So second possible, so here what exactly by increasing the latent space, what it is saying? So this gives the model more capacity to capture more meaningful factors separately. So more latent space means more information is captured, therefore there is a better reconstruction and there is a lower reconstruction loss. So second possible solution is tune that beta value. So how is that you tune the beta value? We have seen some time back, if the beta value is very large, then the quality reconstruction is very poor. So if the beta value is very large, then there is more enforce on KL term, which means the mean should remain more closer, then which means we get Z as very weak Z. If that Z is very weak, reconstruction loss increases. So this also cannot be the solution. You cannot have beta value very large. What is the solution here? The one solution is to choose a moderate beta but not very high. Once again here it is an hyperparameter. So keep changing the values, you will be able to get a balanced between reconstruction and disentanglement. Next is use beta annealing. So the third solution is beta annealing. What is beta annealing? Can we start beta value? So go back to the reconstruction loss and then think, can I have beta value as 0? So when we have beta value as 0, entirely second term becomes 0. So which means you are enforcing the model to learn only, focus only on reconstruction first. Get a good quality reconstruction. Okay. So instead of using a very high beta value, start choosing a beta with a very smaller value and gradually you increase it. So how is that you will be doing? So this allows the model to first learn the good reconstruction and it gradually improves the latent structure. So beta annealing here is beta can start with 0 or a very small value during the initial stage of training. And when the beta value is very small or 0, is it not the second term ideally becomes 0? Then is it not more importance is given only to the first term? First term is reconstruction. So you are first allowing the model to focus on good reconstruction. Then at this particular stage, KL value will be very small or the impact will be very less. So the model focuses only on learning a good reconstruction first. Then gradually increase the beta value. By doing this, then KL term becomes active and starts encouraging the disentanglement. So this is all about this particular concept. With this, we have come to an end of this particular session. In the coming session, we will be looking into a conditional VAE. Thank you.